Hello, in this video we are going to talk about sketching the graph of a function. It looks like this. It has an exponential function involved. Okay, so let's see how we would do this. As before, in the previous videos, we're going to follow our guidelines for doing this. And the first step is to determine the domain of our function. All right, so let's see what we can do here. Um, Here we have a composition of two functions. We have the exponential function e to the x, and we have a polynomial minus x squared. Well, polynomials are defined everywhere, so you don't have to worry about this being undefined. And e to the x is defined for all x. And so the composition is defined for all x. So the domain of this function is all real numbers, or the interval negative infinity to infinity. Great. Let's go to the next step. The next step is to determine the x and y intercepts. It's always easier to start with the y-intercept, I think. So let's think about that. The y-intercept, you just evaluate the function at 0. So if I compute n of 0, what do I get? E to the negative 0 squared is e to the 0, which is 1. Okay, so the y-intercept is the point 0, 1. Easy breezy, cheddar cheesy, right? So next up, the x-intercepts. To find the x-intercepts, we solve the equation n of x equals 0. Well, that's the equation e to the minus x squared equals 0. All right, well, let's think about this. Well, wait a minute. The function e to the x, what does that look like? Let's just think about its graph. We know it looks like this, right? And you notice it has a horizontal asymptote here on the x-axis, and it never actually gets there. It's always positive. Well, if it's always positive, it can never equal 0. This has no solutions, and therefore there are no x-intercepts. Another way to think about that is if you weren't even thinking about the graph and you were to proceed and try to find the x-intercept, what you might try to do is use the inverse function, the natural log, to solve this equation. I would take the natural log of both sides. The natural log of e to the minus x squared equals the natural log of 0. Keep an eye on that. Natural log of e to the minus x squared. Well, natural log and e are inverse functions, so this is just negative x squared. But wait a minute. What's the natural log of 0, or any log of 0? It's undefined. You can't take the log of 0. And so this is another reason. So even if you weren't thinking about the graph, you'd run into a problem right here. You can see there's no solutions. So there's no x-intercepts. Okay, next up, we are going to evaluate the limits at infinity and negative infinity to determine the end behavior and see if we can pick up any horizontal asymptotes for our function. All right, so here we are. Let's see, limit at infinity. Okay, well, the limit at infinity, if I let x go to infinity, what's going on here? Well, let's think again about the graph of our function e to the x. That's the one we should be familiar with. Here's y equals e to the x. Now, when I let x go to infinity in this function, negative x squared is going to negative infinity. So that's like going this direction on the e to the x graph. And what's that going to? Well, that's going off down to 0. So the limit as x goes to infinity of e to the minus x squared is 0. What about the limit as x goes to negative infinity? Well, if I let x go to negative infinity here, negative x squared, well, I'm squaring it, so it doesn't matter that x is negative. This negative x squared is still going to negative infinity. If I plug in some thing going to negative infinity up here in place of x, I see I'm going off to the left. So again, it's going to 0. So whether I go to the right or to the left, I'm approaching 0. And what that means is that y equals 0 is a horizontal asymptote. Okay, the next step is to look for where the function has vertical asymptotes. The vertical asymptotes are determined by numbers a, where the limit of the function approaches infinity or negative infinity. Let's see where that can happen. So we want to find values of x where this approaches positive or negative infinity. Well, if we look over to e to the x, we see it never goes to negative infinity. The lowest it ever gets is 0. But it does go to positive infinity. But how can it go to positive infinity? Well, it goes to positive infinity when x goes to infinity, when the argument up here in the exponent goes to infinity. Okay, let's look back at this. Can the argument up here ever go to positive infinity? Well, no. Look, it's negative x squared. The biggest it can get is 0, right? It's always non-negative because it's negative something squared. So there's no way this can ever go to positive infinity, and so therefore there's no way that this expression can have any vertical asymptotes. Next up, let's compute the derivative of our function and find the critical numbers, and then use those to determine the intervals where the function is increasing or decreasing. And we'll also see if we can find the local extrema using the first derivative test. Okay, so we have to compute the derivative. All right, well, this is just a matter of applying the chain rule, so good exercise. You should pause the video now, compute the derivative, and check your answer with mine. Well, this is the derivative that I got, all right? So we want to check the intervals of increase and decrease. So we want to look at the sign of this function. And to find when it's positive or negative, we will need to look to see where it's 0 or undefined, right? Those are the critical numbers. Well, this thing, can it ever be undefined? Well, this is a polynomial. It's defined everywhere. This is defined everywhere, and e to the x is defined everywhere. Everything's defined everywhere, so this is defined everywhere. There are no points where it's undefined. What about where it's 0? Well, e to the x is never equal to 0, so this thing can never be equal to 0. What about this thing? Well, yes, this can be 0. This is 0 when x is 0. So that's our only critical number, x equals 0. So we're going to use that to split up the real number line. And then we're going to look at the sign, positive or negative, of n prime. All right, well, to the left of 0, when x is negative, then this thing is positive. And we know this is always positive. And so we have positive times positive is positive. What about when x is positive over here? Well, if x is positive, this is negative. We know this is always positive. Negative times positive is negative. So what we see here is that the function n is increasing on the interval negative infinity to 0, and n is decreasing on the interval 0 to infinity. Now, what about applying the first derivative test? Well, if we have a point on the graph, and to the left of the point the function's increasing, and to the right it's decreasing, let's see, it's increasing and then it's decreasing, and that's a point on the graph. We know the function's defined at 0, because it's defined everywhere. Well, look, that's a local maximum. This is what the first derivative tells us. If a function's defined somewhere, increasing to the left and decreasing to the right, it has a local maximum at that point. And so our function has a local maximum at 0. You might even be interested to know what the value is at that local maximum. And to do that, you would just plug 0 into the function. But we did this in a previous step. That is the y-intercept, right? And we got 1 as the answer. So we know 0, 1 is the local maximum for our function. Finally, we're going to do step 6 here. We're going to calculate the second derivative to determine the intervals where the function is concave up or concave down. We're also going to see if we can identify some inflection points, points where the function changes concavity. And we're going to see if we can use the second derivative test to double check what we found in step 5 for the local maximums and minimums. Okay, so we need to compute the second derivative. So let me rewrite down the first derivative, and we'll compute the second derivative. I'm not going to go through the steps here. There's a couple steps and then a simplification. You should do that on your own and then check your answer with me. So pause the video now, do that on your own. And here's the answer that I got. Okay, so there we have the second derivative. Now what we want to do is we want to find where n double prime is positive and negative. So what we're going to do is look to see where it's 0 or undefined. Well, this is polynomial is defined everywhere. This is defined everywhere, so it's defined everywhere. What about where it's 0? Well, this term is never 0, but this can be equal to 0. So let's solve that. Well, when is this going to be equal to 0? It's when x squared is equal to a half. Well, if x squared is equal to a half, that means that x is equal to plus or minus the square root of a half. And if you wanted, you could write this as plus or minus root 2 over 2, rationalizing the denominator. But I'm going to actually write it as plus or minus root 1/2 because I just think it's easier to work with in that form. And what are we after? We're looking for to see where n double prime is positive or negative. So these are splitting up the number line into intervals that we have to check. Okay, so you can see that we have 1, 2, 3 intervals we need to check. So let's look over here to the right. When x is greater than the square root of 1/2, what is the sign of n double prime? Well, we know that this thing is always positive. And if x is greater than the square root of 1/2, then this is greater than 2. So when I subtract 2 from it, it's positive. So positive number times a positive number is positive. Now what about when x is between these numbers? Well, if x is between these numbers, then, well, that means that x is between 0 and 1/2, right? So that means that this is between 0 and 2, which means when I subtract 2 from it, I get a negative number. And this, like we said, is always positive. So negative times a positive is negative. And what about when we're to the left of negative root 1/2? Well, we're squaring x, right? So that's the same as being to the right of positive root 1/2. So we get the same result that we got over here. This is positive. Well, what is this telling us? This is telling us the concavity of n. So we can see that n is concave up on the interval negative infinity to negative root 1/2, union root 1/2 to infinity. And we can see that n is concave down on the interval negative root 1/2 to root 1/2. Now, can we say anything about inflection points? Well, inflection points are points on the graph where the concavity changes. Well, we can see that the function changed from being concave up to concave down at negative root 1/2. Now, is that a point on the graph? Well, sure, because the function is defined here. So if the function is defined here, this does correspond to a point on the graph. What is the point? I get the y-coordinate by plugging this in for x. If I plug negative root 1/2 in for x, I get negative e to the negative 1/2. So one of the inflection points is the point negative root 1/2 comma e to the negative 1/2. I have another inflection point corresponding to this value of x. And the y value is what I get when I plug this in for x. And I get the same thing, e to the negative 1/2. So another inflection point is the point root 1/2 comma e to the negative 1/2. And finally, we can talk about the second derivative test. Remember that we noted that the first derivative was 0 when x was 0. The second derivative test says if you know the first derivative is 0, and you know this function is concave down there, which it is, then you have a local maximum. So this corresponds to what we saw before in the previous step when we used the first derivative test. Just another way to get at the same answer. So we have a local maximum at x equals 0. Okay, so finally, let's sketch the graph of our function. So let's sketch some axes here. Notice when I'm making my axes, I'm keeping in mind some of the properties of the function. I know the function's always positive, so I don't need to sketch much down here. So I'm going to skew my axes to be more focused towards the positive y-axis than the negative. Now, what is one of the things that we found out? We found out that the y-intercept was the point 0, 1. So we can plot that point right here. We saw there were no x-intercepts, so there's no x-intercepts to plot. We did find that y equals 0 is a horizontal asymptote. Well, that's this line. That's the x-axis. So that's a horizontal asymptote. And what else did we find? We learned that the function has a local maximum at x equals 0. So I know that the function will be curving downwards right here. We also learned that the function is decreasing to the right of 0, and it's increasing to the left of 0. So we know it's increasing here. And we know it can't dip below the x-axis because we'd have an x-intercept. So it has to somehow be increasing and go off to the left. And this is an asymptote. So all those things together tell us that it has to look something like this. And to the right, it has to be decreasing and have that as an asymptote, and it can't cross the x-axis. So we see it looks something like this. Now, what about that information with n double prime, the concavity? Well, you can see that it changes from concave down to concave up here, the way we've drawn it. Where did that happen? Those were those points that, the inflection points that we found. Those happened at positive root 1/2 and negative root 1/2. Those gave us the inflection points over here. So this is a sketch of the graph of our function. And this is actually very similar to the normal distribution function from statistics. In fact, this is essentially what it is. It's just got a few other parameters in here, which are just constants that adjust this for statistical properties. But this is the graph of e to the minus x squared.